What would you think of me if I say that calculating the bracing force in a pre-engineered building is not really that hard and it's just as simple as multiplying some values in your calculator? It is insane, right? But believe me guys, it is one of the easiest thing in the entire design process and we are going to unfold that in this video. Hey everyone, welcome back to the channel. If you are new here, my name is Parshit Jayan. I am a structural engineer based on Pondicherry, and on this channel we discuss about various tools, concepts and methodologies to help engineers to work productively and efficiently. Today we are going to discuss the process of force transfer in the bracing system. The video is subdivided into 4 sessions. Firstly, the load arm force path. In this session, we will be discussing how the wind load transfers from the point of contact to the bracings. And secondly, the behavior of bracing. This session is mainly about the behavior. So, upon the application of the wind load, how the bracings behave to resist the force. And the third session is going to be bracing force calculation, a manual calculation with an example. And finally, we are going to verify the manual bracing calculation which we did with the STAAD model. In addition, we have a bonus content in between the session as well. So stay packed. Moving to the first part, which is the load or force part. If we consider a typical pre-engineered building, something like this, the wind load may be applied on the lateral or the longitudinal direction. The wind being applied on the lateral direction is resisted by the A-type frame. So, hope there is no doubt about it. Now, moving on to the other direction, that is the longitudinal direction, the bracings are the structural systems that resist these loads. But how they resist, we are about to unfold the answer for that question soon. Now, what is the load path that the wind takes to reach the bracing? As we see our building, it is completely cladded. Cladded is a technical term to say that the building is fully covered with sheeting. So, in the times of heavy wind, the first one to get in contact with the actual wind is the wall sheeting, right? Now, when this sheeting is pushed or pulled by the wind, usually it won't come off, right? Because it is firmly attached to the wall girts. So, these wall girts in turn attach to the wind column through the girt clips. Now, the load reaches the wind column. If you see, the bottom of the wind column is connected to the pedestal column through anchor bolts, and the top, it is connected to the rafter. So, the load which is reached the wind column will be shared between these 2 points of contact as reactions. We don't worry about the load which reaches the bottom because it is passed on to the pedestal column, but the wind reaction which is at the top needs to be properly diverted back to the ground. To achieve this, we use bracing system. In simple words, the load path would be sheeting, wall girts, wind column and bracings. That's all about the load path. Now, we have reached the second part of a video, which is behavior of bracings. For our understanding, let's consider this building. The load which reached the top of the rafter will try to push or pull the rafter at that point. Let's consider it is going to push the rafter. How does our bracing behave for that action? Before moving on to that, you guys should be aware that for the applied load, only one pair of a bracing would be active. What does it mean? Which means either these bracings will be active or these will be active, but not the both. Why it is so? The reason is, say the wind load is pushing the rafter. These pair of rods would be subjected to compressive force. What happens if you try to push a very slender member? It will buckle away, right? The same thing happens here as well. These 2 rods would buckle away and the force flows along this line to the next rafter. From there, when it tries to escape, these two tie members will not allow the rafter to move further through their tension action. So, the force applied at this point reaches the next rafter, and from there, these two bracing members take the force through the tensile behavior. That's why the X bracings are termed to be tension bracings, as they take the load through the tensile behavior. These forces will then move downward to the eve point, and from there to the wall bracing, and finally to the support. To summarize, only one pair of X brace would be effective for the applied load, and they transfer the force through their tensile behavior. Before moving on to the third part of a video, there is a bonus information available regarding how to decide the number of brace bays and their position of brace bays and so on. So, how to decide the number of brace bays? As per IS 800 class 3.10.3.2, the maximum spacing between two braced bay centers should be restricted to 50 mm. So, if you have a building of length 80 meter, then probably we might require 3 braced bays. Now, the second question: how to decide the position of the braced bays? As we have gone through the behavior, the wind load which reaches the top of the rafter travels through the strut tube along that line, right? So, we need to place the bracings as near to our end frames such that a portion of a wind load which comes is immediately resolved to the ground. And from there on, through the required number of bracings, we can evenly space them apart without restricting the maximum spacing, that is 50 meter. So, if we take an example of 80 meter, we can provide one bracing at each end base and the other at the middle of the building. In addition, if there are n number of brace bays, how force would be distributed? Considering the stiffness of the brace base be the same, the load will be equally distributed to all the braced bays. Moving on to the next session, that is the bracing force calculation. For the simplicity of the calculation, let's consider this building. As we see, since the length of a building is less than 50 meter, we got 2 brace bays. And in order to efficiently transfer the force, we place them at the end base. Now, let's consider the required parameter to calculate the bracing force. Let's say the wind pressure is 1.89 kN per square meter, wind load coefficient is 0.9, the tributary area of the wind column is 7.5, and the height of the column is 6.5 meter. So, the wind load that is going to act on the wind column as UDL would be 1.89 into 0.9 into 7.5, which is nothing but the pressure into coefficient into tributary area, which equals 12.76 kN per meter. Now, these UDL need to be converted to the reaction at the top and bottom end of the wind column. In order to do that, we need to multiply this value with the length of the member, and we need to divide the value by 2. So, force at the rafter location is equal to 12.76 into 6.5, which is height of the column, divided by 2, which equals 41.47 kN. So, this 41.47 kN passes through the strut member, and as it reaches the next rafter, the bracing get into action. Since there are 2 brace bays, each bracing system will take an equal amount of force. That is, each brace bay will take 20.735 kN, the total force divided by number of brace bays. And then this 20.735 kN is resisted by these 2 bracing rods, right? So this 20.735 in turn is getting divided by 2. So our brace rod force would be 10.37 kN. As these rods are oriented diagonally, we need to resolve the force which is traveling straight to the direction of the bracing. So considering the bracing make 45 degree with the strut tube, bracing force is equal to 10.37 divided by cos 45 degree, which is equal to 14.66 kilonewton, and that's our bracing force. So 20.735 and our bracing force would be 14.66 kilonewton. Moving forward to the last part of the video, which is verification of the manual calculation with STAAD model. The 3D STAAD model of a building we discussed is here, with the wind load applied on the wind column. So we have calculated it is 12.76 kilonewton meter. Let's visually verify how the load is being passed on to the each member. I have already analyzed the frame, so I am going directly to the post processing, to the beam results. I am switching off the diagrams. So as per our calculation, this member should have a force of around 41.47 kilonewton. So if I just click that member, and yeah, it is having a force of 41.328. So when this force reaches this particular rafter, it has to be halved and then passed on to the next line. So this has to be around 20.735. So what we are getting is 20.244, and from there these brace base should equally contribute and around 14 kilonewton, right? So yeah, it is 14.75. What we calculated is 14.66. So 14.75. And as we have mentioned in the behavior of bracing, so this particular bracing should not carry any forces, so they should buckle away. As you see, they don't carry any forces, or they are inactive for the applied load. So only this pair of bracing is active, and all the values are matching with our manual calculation. What you gain from this video could be very critical to analyze the behavior of the bracing system. Hope I made my points very clear. If at all there is any query or doubt regarding this, you can go write your queries in the comment section, and we'll try to answer all the queries. And if you have any suggestions or topics to be covered on steel warehouse design or automation, comment them out as well. And if you like this video, give a thumbs up and subscribe to the channel so that you don't miss my new videos. Until then, it's bye from Parshit Jayan.